Now I'm going on to a second example of Le Chatelier's principle. You can see this on your handout, example 2, pH paper in ammonium carbonate test tube. I'm using the system you had in last week's lab to demonstrate a shift in equilibrium in a chemical system. This is ammonium carbonate salt. This is a piece of pH paper, which is orange. And I'll introduce that into the tube, and you can see that a color change occurs. This is actually an equilibrium occurring on the pH paper that's making this green color appear. We can describe this equilibrium using chemical equations with two arrows. To begin this discussion, I'll draw a strip of pH paper in the tube. In the bottom of the tube was the salt. So you can label this ammonium carbonate. Ammonium carbonate. When the paper is at the top of the tube, then you get this light green color that appears here. And that color can be explained molecularly. So here I'll zoom in on the actual paper, and we'll look at what does that mean. So in your lab, you should recognize that we have an equilibrium occurring, which could be expressed this way. Hx, which is orange, NH3 is a base that's colorless. X minus is green. NH4 plus is colorless. So this is the chemistry that occurs in the test tube here. NH3 gas does climb up the tube here. NH3 gas comes out of the salt, and the vapors partially fill the tube. Now the reaction on the pH paper results in this equilibrium as sketched here. So you can imagine that there are HX molecules on the paper which are orange. There are also the green form, which is the X minus NH4 plus. NH4 plus is not green, but the X minus is green. And on the paper, this is what creates that greenish color seen here. So this is pale green. For every molecule of HX that turns into X minus, which is constantly occurring in this tube, you've got your NH3s floating around. They are contacting the paper. When NH3 contacts the paper, it could react with the HX and turn into this green state. But for every one of those reactions that occurs, one of these in the green state reverts. So look at this arrow coming back. Reverts to the orange state of HX, and the NH3 would just leave the paper. So although this picture here is static, you have a dynamic equilibrium where molecules are constantly reacting. No net change, so it stays a fairly constant pale green color. This equilibrium can be shifted if we drop the paper further into the tube. So you can see now at the bottom, this paper here is much darker green than the paper toward the top of the tube. So the equilibrium has been shifted down here because the concentration of ammonia near the salt itself is much higher
than the concentration at the top of the tube. Once again, we can show what's happening with a chemical equation with two arrows.
Alright, scenario number 2 is when the paper was dropped into the bottom of the tube. Here's the salt, again, ammonium carbonate at the bottom. Now we can go ahead and sketch the piece of paper way down here, right? So here the paper gets much greener. So I'm drawing it as a darker green color. You can label it dark green. The reason the equilibrium has shifted is because if you were to look here at the bottom of the tube, the concentration of NH3 is much higher at the bottom of the tube. So as we get to the top of the tube, they're spreading out. This is a high concentration of ammonia right next to the salt. And this is classic Le Chatelier, where you say the conditions have changed. We have altered the conditions to have a higher concentration of ammonia. How does that affect the equilibrium? So now if we look at the pH paper molecularly, here's the pH paper. I'm going to draw this one with still one HX molecule. The number of HX molecules is diminished from the original equilibrium, but there won't be zero. They'll just be greatly diminished. And then I'll have most of them in this green state where the ammonia has, in a sense, exposed the color of X. Okay, so that's a reasonable representation of the molecular equilibrium on the pH paper. You can see most are in the green state. That's what gives you this dark green color. There'll still be an occasional one that's in the HX state. This can be explained with arrows. HX is reacting with the colorless NH3. But in this case, I'll draw the NH3 as this enormous NH3 to represent the high concentration. In a sense, that makes a kind of a pressure going this direction. So the rate of reaction leading to the green state is greatly enhanced. That's what this big arrow means. Greatly enhanced rate going to that way, because essentially the paper is being bombarded by NH3 molecules. So the HX has a very hard time hanging on to its proton. The rate coming back still exists. It's a normal sized arrow, and that's why there will always be a few of these HX molecules in existence. They just don't last very long in that state. They quickly get converted back to the green state. That's why perhaps 95% are in the green state, 5% in the orange state. Maybe 95% in this state, maybe 5% in this state. All right, so the equilibrium has shifted to the right because of the increased concentration of the NH3. How about due to increased concentration of NH3? Period. Change the conditions, increase the concentration, equilibrium shifts in a predictable fashion, leading away from the increased concentration.
Here are the two pieces of pH paper. This one's from the bottom of the tube, this one's from the top. You can see the colors are quite different. But now another shift in equilibrium is occurring because they're exposed to the air, which is devoid of ammonia. And so now you can see that the original orange color is coming back here. So this again can be explained with chemical equations with two arrows. We've changed the conditions. The equilibrium shifts accordingly. So now you can see they're back to their orange color. A couple minutes have passed.
Scenario number 3 talks about when you take the pH paper out of the test tube. So here's the original pH paper in the test tube, and then it comes out of the tube. In the tube, it has that light green color. And out of the tube, it turns into just plain orange pH paper. There's no green left. So now I'm zooming in so we can see the molecules. I'm going to draw the two pictures. So I'm actually going to let this one be the orange one on the left. It'll match my original equation if I do that. So here's HX, 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 HX. This is the orange state, which is the ending state. The original state will be the green state, light green, and that has some molecules in this green color. And some molecules in the orange state, HX, HX. So taking the pH paper out of the tube converts it from this green state to the orange state. Let's go back to the chemical equation and see what's happening here. We have HX reacting with ammonia, but the idea of taking it out of the tube is that the ammonia is really low here. Essentially zero, because the NH3 is drifting off into space. And so if you say, what is the concentration of ammonia near the pH paper, it's essentially zero here. I'll say it this way, very low NH3 concentration outside the tube. So inside there was a decent concentration of NH3, which got very high near the bottom of the tube. But outside the concentration is almost zero. So I've drawn a tiny, tiny NH3 here. On the other side of the equation, NH4 plus and the green X minus. So NH4 plus and X minus on this paper here can react with each other. So I'm drawing a nice healthy arrow coming to the left. But essentially, since there is almost no NH3, the arrow going to the right is minimal, perhaps even non-existent. You can make an argument for non-existent because the NH3 leaves the vicinity of the paper. So in this situation, you should see a shift to the left, a marked shift to the left. If you wanted to anthropomorphize, you could say it's to fill the hole, but this is a never-ending struggle to fill the hole. there is no NH3. So since there is no closed container, since the NH3 can drift off, then it's impossible to fill the hole. It's impossible to restore the NH3. But Le Chatelier's principle would suggest the equilibrium shifts in the direction to moderate the change. If the NH3 is gone, try to replenish. Try to replenish. Nature can't replenish in this case. Leaving you with nearly everything in this state, so I'll put 99+% on the left, less than 1% on the right. It goes to 0 essentially. That's a shift in equilibrium due to a change in concentration. It's like when we pulled the blue out of the cylinder. Nature shifts to try to replenish that. In the cylinder it could replenish. In this case it can't.
So in this environment, equilibrium favors the green state. In this environment, equilibrium favors the orange state. In this environment, we're kind of halfway between those two states. And this is an example of Le Chatelier's principle, shifting equilibrium based on the conditions, the environment, the concentrations of the species present in the equilibrium.